Okay, so good morning. Welcome to the second day, and so we'll have like two sessions again, like previous day. So let me just welcome Abhishek to chair this session. So Abhishek, over to you.
Still 1 or 2 minutes left.
Something like
1 minute, 2 minutes. We'll wait 2 minutes.
And
Start
I
at
think
least 1 minute. Okay. Good morning, everyone, and welcome to this first session in the second day. So we have two speakers in the morning. The first speaker is Oyen Banerjee from Mysore, Kolkata, and he'll be talking about long title. So should I remind you at some point?
I think so, of course.
35 minutes. So it's 40 plus 5. I'll remind you at 30.
Okay, is this good? People at the back, this is good? Okay, I need to take the... So this is quite a stage. Pretty impressive setup, nice lights as well. It is, of course, this is the second time I am coming here. The first time I came was when Ronojoy was around. Now, of course, he is settled in probably greener pastures. And it's also very nice to see a lot of old friends out here, especially from IISc, though, of course, they are all mostly younger to me. I think Pinaki and Shamriddhi and Shauroji, I did have encounters with them. There's some overlap with them at IISc. The one person, of course, is somewhat senior who was there when I was around, and this is the chair of today's session, Abhishek, and we used to call him Dabhi then because that was his email. And of course, he was known as a person who just worked and did things that I had no clue about. I am also doing things now on which I had absolutely no clue about when I was doing my PhD. And that is what I have the temerity to talk about those things. So please bear with me. This was never my focus area, but as days evolve and you evolve, you pick up things. And especially when you have nice students to teach you, I think one does make some progress. So this is what I'm going to talk about today, unraveling some method in these apparent madness of fluctuations that you have in the mesoscopic world of small particles. And the reason that these fascinate me completely is that finally life is made of these small fluctuating entities, which are of course living. And of course physicists, humanity has very, very little clue about how these things really work and how they themselves are living and walking around. And these billions of molecular motors, which are always and continuously doing work fantastically efficiently. And we try to study them, and we try to mimic them and perhaps understand how they are so good. So that is of course a long-term thing that we ought to have. And I come from IISc Kolkata, and the lab is called the Light Matter Lab. And these are the students who have developed what I'm going to talk to you about. And this is this guy. Two of them are here, Shubhajit and Vishwajit. So this guy is the person who really set this all up. Another person, of course, he's just next door, IIT Madras, Basudeb. He was the first graduate out of the lab, and he's now grown big and associate and all that, professor. He had just done a little bit of sort of the tip of the iceberg, but it was Shubhajit who took it on, and he then of course moved on to Germany, and now again he's back, and he's going to give a talk here on Saturday, and on the 20th, last day. And unfortunately, I'll not be there to egg him on, so I request all of you to hear what he has to say. Vishwajit has a poster outside. Anisha is the youngest, kid in the lab. She's just sort of starting about 1 year down. These two, Shubhra Kohli and Obijit, are the ones who have all finished, and they're off. And so Shubhra was actually the guy, both are in Germany, who started working on this non-equilibrium stuff. Shubhajit had set up stuff which was still more equilibrium dynamics. So now, just yesterday, I guess, one of the old friends, Sharojit. So the image that I have in IS is the guy who worked in Vasant's lab and was lasers doing these things with atoms and ions and trying to measure whatever frequency. That part frequencies were not known. What I did, what was known was we worked in atoms and ions and tried to cool them. So lasers, this was called the laser lab, and I have an association with lasers, of course, and that image, of course, still sticks. So he asked me in Bengali, so that effect will not come, but when I reproduce this, what he said was, are you still with laser taser? So yes, I do work with lasers in optical tweezers, but there are a lot of tasers around, and very, very diverse things, which start right from very exotic properties of light that are revealed through optical tweezers, that is spin-orbit interaction, where light, angular momentum, spin angular and orbital angular momentum can basically couple and create some extremely exotic effects. This is something that we are very proud of. We have developed in our lab, by the way. So this was written by that technology we have, which it's a bubble which sort of moves when I move my laser, and it also patterns as it moves. So any material that is there in the fluid actually self-assembles and forms permanent patterns. You see this is 2 microns, this is ISA written, and we call this microbubble lithography. And this, of course, has helped us in also creating some very nice non-equilibrium conditions in the lab, which we actually use to do this, statistical mechanics of mesosystems. This is again something very different. This is trapping of particles using photophoretic forces, which is not really optical dipole forces. And these create very stable traps, and these are actually, this work we have developed not using commercial microscopes, which I hope some of you at least are aware of, are typically used for optical tweezers. So this is a setup that we have entirely developed, and this is also a complete gold mine for non-equilibrium stuff, because it is trapping using heat and trapping very, very efficiently using heat and air. And in air, it's very, very difficult to trap things. By the way, so this is optical tweezers. So that is what the lab completely focuses on. Optical tweezers, we have now about 4 optical tweezers in the lab, out of which all of them are employed for different things. The last one is not really tweezers, but it is essentially we make these waveguides out of these biomimicking, mostly peptides and all, and they show some very fascinating properties in terms of light guiding and all that. So that is something which we have started about 3-4 years back. But of course, today's story is on this, and I like to tell stories, and what I will tell you is, of course, the journey that we have taken for the last about 6 or 7 years. And what I will stress upon are the experimental nuances, because I know people here, this is a focused conference on non-equilibrium dynamics, and I am not somebody who is in the theory. I've been doing it, last 5-6 years. So I know there are people here who are much better aware of the theory than myself. But in India, as is the tragedy, I may say, experiments are not something that we really are specializing in. And I think, with the exception of our lab, we probably have Rajesh and Pawan and Vijay at Pune. Very few people are really working with optical tweezers and in this domain experimental stuff. So I'm going to really tell you how difficult, not difficult, easy. I mean, what are the things that you do in experiments in order to make any measurements of these very tiny measurements of particles actually fluctuating, and most importantly, finding out generic patterns, because that is what is most important, because these are very small particles and their trajectories or the fluctuations are even smaller. So unless you can measure reliably, what you're going to get and what you're going to conclude is going to be disastrous. So that what you do in order to get to that is mostly what I'll focus on. And of course, incidentally, what we have done, the physics also would, of course, come out as a result of that. So this whole thing started when I think Basudev was looking at, 2 particles trapped in 2 optical traps and 2 optical tweezers. And trying to see if one moved, how would the other respond? In the sense, he was giving a sort of a square wave and looking at the displacement of the other particle and seeing that optical tweezers, of course, uses focused light to trap particles. That I'm not going to tell you in detail. If you're interested, a lot of stuff available, but essentially it uses optical gradient forces. Dipole forces, there are two things, gradient and scattering. Gradient forces help you to trap, scattering is destabilizing. But so you have a trap time constant, which is dominated by your trap stiffness, gamma by k. This gamma is the viscosity, k is the stiffness. So there is a time constant. And there is if you give a square wave, then that also has it has a rise and fall. So you will look at things, how the motion of the other one is getting affected. Shubhajit took it off. So by the way, besides, I'm just jumping a bit. So here, of course, is the wondrous world of mesoscopic particles, and why these are interesting is these actually do work. So you have a ratchet here, and you have this, these are birefringent particles, and these are rotating, and there's a flow, and these things go by. There's another particle which just really goes around. So this is interesting, as I said, because this is how life works. This is, for example, for sperm cell. This is a kinesin working, and then this is fluctuations, of course, that we actually measure. This is entropy, probability distribution. This is the work probability. Our contribution is that we have these bubbles which move, and you pump in heat. Therefore, it is non-equilibrium. It creates flows and flows of liquid. And if you have a particle trapped close to it, that particle feels a very, very interesting environment. However, coming back to the story, what we really wanted to look is at a coupled pendulum. Coupled pendulums are trivial, of course, if you're doing them in air because of the inertia. In an overdamped system, which is optical tweezers, they will not work because the mass is gone. The mass is damped out, right? However, there is still water that has a certain viscosity, of course, friction. So the question was that we wanted to ask was, what happens if I take this system in water? And how does it look like? This. You have this particle trapped. This particle is driven, and this is how it really looks like. This is schematically, cartoon. So we were doing this. Shubhajit, however, did not give a square wave. He gave a sine wave. And then in a lab meeting, he excitedly told me that as he was changing the frequency of drive of this particle, this guy was responding differently, which was not expected. This was showing a resonance-like phenomena, which was not at all expected because this is a highly overdamped system. Only thing was we kept these very, very close. We kept this. So these are like 3 micron particles. The surface-to-surface gap is 1 micron, only 1 micron. Very close, and people had not done this before. People had looked at the system but not come this close. And that gave some pretty interesting, started a story. Okay, this was still an equilibrium system, and of course fluctuation dissipation holds. And we studied the mutual cross correlations and all that. But most importantly, we found clear signatures of a resonance in the motion of the second particle because the first particle was driving it as a response. And you could actually tune the width of the resonance pretty fascinatingly. So in air, of course, you know that if your damping is lower, the resonance gets sharper. Here, this is a resonance driven by friction. And if you actually increase the friction, you get narrower widths. So that is quite fascinating. But there is interesting thing is that if you now want to tune the resonance peak frequency, that does not happen easily if you have a liquid with higher friction, with viscosity, right? So we use this as a very nice tool for doing 2-point macrorheology. Because 2-point microrheology essentially is measuring the viscosity of these solutions of liquids at very, very small length scales. And this is different from bulk rheology because bulk will give you an overall property. I mean, rheometers typically will give you bulk rheology. But actually, if you try to do these, at like micron length scales, and then try to verify with a rheometer, you probably can get different things because any kind of inhomogenities, any density fluctuations will not be picked up by the rheometer, but it will just average all over the place, and this one will actually pick up. So we published this. We of course tried PRL, and the comments were essentially why this cannot be published as PRL is that this is not non-equilibrium. because these are still an equilibrium system. We've done a good job in terms of really studying and providing the groundwork of then going on to more interesting territories. And this second one, of course, to measure viscosity, we could measure at like very high accuracy and a very, very large dynamic range in terms of viscosity of solutions. So that started off this quest. And how we made this non-equilibrium was, of course, by the way, I forgot to talk, I had written my collaborators, so most of this non-equilibrium theoretical support has come from people at Nordita. Supriya Krishnamurthy and Srikant, her very, very talented, Srikant Manikandan, her extremely talented student who's now at Stanford doing his postdoc. And there is a third person who is one of the organizers here, Ornob Pal, whom we've started working with. And Ornob has a paper here, which is basically doing this. Only thing is, the difference that he has, that they looked at, is that this drive is no longer by a sine wave. The center of the trap is now moved by noise. It is modulated by a correlated Ornstein-Uhlenbeck noise. And he published this in 2013, and we have taken it and we have done all kinds of nice things with it. This is now a completely non-equilibrium system. You have some kind of an effective temperature, and most interestingly, you have, this is lambda, is the variable which describes the trap center motion, and it is, the correlation is basically exponential. So that gives you a very different handle. This is a handle to control the non-equilibriumness as well, which you can do by controlling this amplitude of A. And you also get an effective temperature, which is A tau 0, which I'm going to just talk about now. So how do you find signatures of non-equilibriumness? One big thing is that entropy is generated. So how do you measure this entropy? If for equilibrium systems, for long run, you do not have, if you average over long enough time, you do not get any entropy. Non-equilibrium you get, and the classic strategy for measuring that is by looking at the probability. If you take a time series, probability of, in the forward direction, divide that by the probability in the backward direction, and just take a log and all. This is the classic way of doing it. This has some issues because, first of all, generating this probability distribution function for complex systems, it is not easy. For example, as a complex system as a kinesin moto, or say this particle that is trapped near a flow of a bubble, it's not easy, right? The dynamics analytically doing is very tough, getting this thing. The other part is that you need very long time series. And if you are doing your work with an optical trap, you need to hold the particle for a very long time in an absolutely identical condition. The particle, the environment should not change. That is not simple at all, right? So this was like, this is a classical strategy. What I'm going to talk about now, and I've taken some liberty, some poetic license or scientifically poetic license or whatever I can say, is there a quantum-like way? And why I say quantum is that because this, of course, borrows directly from the very, very well-known uncertainty principle given by Mr. Heisenberg, Professor Heisenberg. This is a thermodynamic uncertainty principle, and very much like that very, very well-known uncertainty principle, this too sort of puts bounds on the entropy. And one big thing that it actually relies on is that if you have a non-equilibrium system, you have currents, probability currents, which tells you that in equilibrium, for example, this is PA is the probability of the particle of the state A, AC is the transition probability. The probability of going from A to C and C to A are the same, and the current is 0. Whereas for a non-equilibrium system, that is not the case. Forward and reverse paths are different. And the stronger the non-equilibriumness, the more will be the current, right? And that is exactly what is used. You find these currents. You essentially, then the total entropy is, of course, you relate these transition probabilities using this, very well known. And finally, the total entropy is the sum over all events, all paths. So essentially what it tells you, this uncertainty type relation, is if this is like a lower bound of entropy, and that depends on the mean of the current, the more the current is, and lower the variance is. that will give you a higher bound of the lower, so more entropy is generated, which basically says that there is more directionality in the problem, in the sense there are more currents, higher currents, and the fluctuations are lower. So if you want to have more precise measurements of fluctuation, the system better generate higher entropy. And then our friends Supriya and Srikant, they came up with this great scheme in 2015, where even if you do not know, if you do not solve the trajectory, the dynamics, by just using the trajectory itself, you can come up with an actual measure of this entropy, where they've showed it for these known systems, that this method where you maximize J by a strategy and look at it at t tending to 0, put that as an asymptotic limit, you get the real entropy. The whole thing is, of course, maximizing this, and that is, again, I'm saying somewhat quantum-like, because what you do is you essentially, in a time series, you do a Stratonovich type of this approach product. So you take this, you write this current as some kind of an expansion of basis functions. For me, this is how I try to look at it, simple connections. And this science, you essentially are finding out these coefficients here and maximizing them. And these can be different bases. So you can take linear, you can take polynomial, you can take Gaussian, like what I've shown here. And you keep on doing an iteration technique where you see where the entropy is maximized. And once you do that, you use, and that you do by these either gradient descent or particle swarm techniques, Python basically, these different packages you have in Python. And then you can actually go, you keep on doing this till you find an upper bound, maximize, right? And that, of course, we took, so that paper that I showed you, that was theory. No experiments had been done, okay? So we were the first one to do the experiments to validate this. And that we again used Arnob's baby, that is this stochastic sliding parabola, as we call it, where you have this trap center modulated by an Ornstein-Uhlenbeck noise, correlate noise essentially. Now this is the thing that I would really spend some time on. This is the optical tweezers setup. So you have the trapping laser, you have a detection laser. And these experiments, especially when you do with two particles, is really tough, because you have two different trapping lasers, you have two different detection lasers, and the reason that you do not use the trapping laser to detect is that you do not want the detection signal to change when you change the power of the trapping laser, right? Because if you want to have different trap stiffnesses, you change the trapping laser power. So that is something you keep fixed. We have another detection laser. And especially when you're having two particles very close to each other, you better make sure that no particle or no laser beam talks to each other. Neither trapping beam nor detection beams, because if they do, whatever you are measuring is going to be completely wrong. And remember, you're actually focusing these spots to 1 micron dia, and you're actually getting out information of particles which are moving over tens of nanometers or even less, and you're ensuring that the correlation exists, which is hydrodynamic purely. So the reason that this resonance happens is because there's hydrodynamic interaction. I did not go into details. But you are trying to find out signatures of only that. So you have to ensure that the detection beams don't overlap, nothing. So you use all a mixture of polarization and all that. But importantly, but here, of course, we have not gone to the two particle, territory, which we plan to do anyway. I'll talk about it at the end. So what you have is this this thing called an acousto-optic. In this community, it's known as deflector mostly. When we used to do, measure frequency of atomic transitions, we used to call these as AOMs, acousto-optic modulators, where you actually have these crystals, piezoelectric crystals, where you give these, this large frequencies, and they show this thing, something called a Raman-Nath effect, and you have a diffraction grating of refractive indices in that. This is like a phase grating. So if you can modulate that grating, and that gives you both frequency as well as beam shift. So in this community, of course, people use it only for beam shifting, acousto-optic deflectors they are called. So how do I actually change my trap center that modulation by sine wave or noise or whatever is by giving that same signal to this AOM. So this actually is like a grating, so it gives you a 0 order and a first order, and the first order starts jittering, moving around in the way that you want to. Therefore, this beam basically, these are some beam shaping lenses, and then you have mirrors, you have a polarization beam splitter, which combines the detection laser with the trapping laser. And importantly, you have this dichroic, which actually, dichroic means it reflects one wavelength and transmits another wavelength. You have the detection laser reflected out. This is the second one. Part of it goes to the camera where you look at the particles. This part is crucial because this is finally the detection mechanism which is allowing me to detect with high signal to noise any kind of trajectory which is even very, very small, fluctuations of nanometers and all that. This part is crucial. Okay, so how do you measure trajectories? Video imaging, because you just put a camera, you don't need to do all these difficult setups with this photodiodes and all that. Camera, the issue, however, is that when you want to, so typically our, these normal cameras that this being used to film me, that is like real time 30 hertz. So if you want, if you're sampling only at 30 hertz, your Nyquist criteria is 15 hertz, which means that you will not be able to register motions at bandwidths more than the half of the camera bandwidth. So if you really want high stiffnesses, you typically go to, kilohertz level, and then getting a camera at kilohertz is very expensive. Now, the other way, which gives you much more bandwidth, but it is a pain to align, is using photodiodes because they have much higher bandwidth. So remember, a normal photodiode just gives you a total intensity, just gives you a total power. It does not give you displacement. So if you want displacement, then you have to take an array of photodiodes, or you take something called quadrant detectors, where it's like the whole surface is made up of 4 different quadrants of a circle. These are different photodiodes, and the signals are all differently obtained. You take, you subtract or add, they typically subtract to find out displacements in the X or Y. The problem with those QPDs, as we say, call them, is that the bandwidths are typically not too high. Okay, gain bandwidth is not too high. Better than that is what we do. This is called this part, balance detection, and that actually uses 2 different fast photodiodes. These are easy to get. These are less expensive than QPDs as well. But that is, again, remember, the photodiodes will not give you any displacement, just total. So what we then use is this thing called an edge mirror. And very carefully, you have to ensure that the detection beam is cut partially by the edge mirror, hopefully by 50-50, and part of it is reflected to one photodiode and the other is to the other photodiode, the transmitted one. And then you take a difference and you ensure that these deflections are out of phase, because what you're doing by this balance detection is you're cutting off the common mode noise. If you put the same beam in 2, then you will do nothing. This is a real pain to align because it's very, very small. We are all talking about extremely small dimensions here. And unless you get an out of phase signal, your thing will not work. So, but then it gives you gain bandwidth of like 1 gigahertz, very, very high. So you can really go to extremely high frequencies to measure. What we do, of course, 3 micron particles. Typically the trap stiffness we can vary, 10 to 20. We can probably go higher, but that we are limited at the moment by the laser power. And of course the scattering is a big issue. And then, so what we do, this is very important. This is very important. This figure of our, confidently being able to measure displacements of even a nanometer at about 10 kilohertz, that came after 5 years probably. It's very tough because you would suddenly have the line noise coming in, 50 hertz, and you completely go mad trying to find out where this comes from. Now, the very important thing is, remember, in photodiode you're measuring in voltage. So you have to somehow convert that into displacement. That is not simple because you essentially are doing a conversion, and that conversion you do either by using the fact that the diffusion coefficient of your sample of water or something is known. Then you essentially measure the trajectory, you take the autocorrelation, you take in time domain, you can use the equipartition theorem, you do in frequency domain, you do like a classic Lorentzian analysis, and from there you get fit parameters, and you also get a noise equivalent power in terms of the corner frequency you get an amplitude, and that amplitude is directly related to the diffusion constant, and from that you can get a scaling. What we also do to verify is that we put known voltages to the AOM. We look at the video image. The video image, is calibrated by the software that the microscope company provides us, and that gives very good, that we have verified with the size of particles and all that, and it gives you some kind of a confidence check as to how your, this factor of sensitivity factor, that is your conversion of voltage to nanometer, works. Remember, every time you are changing anything in the sample, you're putting a different sample, putting different viscosity, different concentration of particles or whatever, this has to be redone. Because essentially, this is like a gradient force, it's a dipole force trap. Essentially, refractive index, anything changes, power changes, you have to do it again. So this is tedious. But this is very crucial, because otherwise we are not talking about displacements, we are talking about voltages. Very, very important. So of course, what we then did is, this is again, as I said, the two variables is the displacement and the motion of the trap center. And this is, of course, a white noise. Both of these will always be there. This delta correlated white noise. You measure system trajectories. You see that if I give higher, and this is my temperature, ATR 0, this is an equivalent temperature, and you increase the amount of non-equilibriumness, you actually get a higher spread. The effective temperature is increasing, you get larger spreads. So what did we do then? So this was, again, I think given in Ornov's paper, these ones. And then this is our check. So we use that inference scheme, as I described, for doing entropy. And from that, we actually use, so this is another thing, this is this stochastic force inference method, which has been given just in 2020. I think it's a PRX paper, where actually you calculate entropy from information theory basis, saying that there is a rate at which you can finally transfer information from such systems if you want to measure them. So that gives very reliable measurements as well. So we actually used that also as a check, and these are the bounds from the theory, this red, and so from the SFI model, and we use different basis functions, linear and Gaussian, to find out the total entropy as a function of the noise amplitude, this A or theta, whatever you call it, right? And it is sort of not bad what we saw. So the interesting part, of course, then you can calculate the force fields. I'm not going into these derivations, of course, you can find them done in the paper. You can see that the force fields that you generate by this is the method that we used. This is from the stochastic force inference, which is also, they match pretty well. So now we have sort of set up our test bed. It seems to work. Now comes to the new problem. And the new problem essentially is having a bubble, which, because there are, so remember this bubble we are creating by taking, the sample, how you do trapping in optical tweezers, you make a sample chamber, which is typically a sandwich, two cover slips, glass cover slips, and you put a drop of solution, which a dispersion liquid with having these particles that you want to trap. Here for the bubble, what we do is we keep absorbing particles, okay, and some of them get absorbed at one of the cover slip surfaces, and then you come in with light, very, very strongly focused laser. Remember, the laser is focused using very high numerical aperture or very short focal length lenses, which gives you very tiny focal spots, so enormous intensity, going to like gigawatts per meter square level. And that, because you have absorbing particles, they heat up a lot, and they heat up to a level that they form a bubble. However, because I'm heating at that microscopic area, the whole water doesn't heat up. So the bubble is confined to only where the laser is focused. However, what is important is, if I see this is a 3D simulation, so this is my wall, this is the cover slip, you can say. The lower part of the bubble where the laser is intersecting is hotter than the upper part. As a result, the surface tension is lower in the lower part, higher in the upper part, because it's inversely correlated with temperature. And as a result, the lower part of the bubble wants to expand, the upper part wants to shrink. It creates some kind of force. This is called Marangoni flow. And because water is displaced near the bubble, more water comes in from outside, and you get continuous flows both axially and radially. which means that this particle, when I trap it without a bubble, of course it is just a normal particle, and I use the trap center is modulated, but the moment I have a bubble, there are flows inwards. So which means that if I'll show you later, when you do a probability distribution, you can see, well, of course, this green is now the trajectory. You can see that it is more confined in the direction of the bubble. This is the direction of the bubble, right? Because now you have a continuous force there, a continuous sort of drag of the diffusion constant has changed, you can say. And because there is a continuous outward sort of a pull, the trap wants to pull it back. So the effective stiffness increases. As a result, the displacement shrinks. This is in terms of, and you can see the force fields. Green is the one with the bubble, red is without. Now, important is, this is a very difficult problem to solve analytically, because you need to model that. You put an analytical expression for that, that flow, and you probably need to solve the Navier-Stokes equation with unsteadiness and all, which is very tough. You measure trajectories, draw the current, do that maximization scheme. It is very much sort of possible to do. And importantly, this is the level we set for entropy that was without, the entropy generated without the bubble. And what we see is that you expect, because there is more direction in the problem, entropy would reduce. And that is exactly what you see by the method, our inference scheme, when you go closer to the bubble. As you come outer and outer, you actually see that as you go farther from the bubble, its effect reduces, and you tend to approach the situation with no bubble. And we try to sort of, again, Srikanth et al. Did the modeling part. So instead of, this is the classic equation, this is the flow that comes with the bubble. Lambda, that is the trap center, doesn't change. However, there is the resultant, the time scale does change for the bubble. Okay, 5 minutes only, my goodness. 5 plus 5, okay, so I'll really rush. So that changes, the time constant and the diffusion constant both change, and we sort of use this A and B as fitting parameters, and you get, this is like, well, it does seem to asymptotically approach the no bubble case. So this gives us some confidence, and then this was the paper. Then the next things, I really need to hurry now. So again, these are just the results. I think I have set up some kind of a platform. So this skewness, so what is this? So fluctuations are crucial, and these fluctuation theorems, however, they set like some bound to the fluctuations. But what also is known that if you look at fluctuations, if you have any non-equilibrium phenomena, then the time that, the time scales for which the fluctuations are above the average are actually, they were shown by Levy to obey some arc-sine law. So at long time scales, they are more probable, something like that. Then, what is interesting, that this is at when you're looking at very high time scales. You know that the time that this fluctuation the particle spends at above average is going to be dictated by a sine law, arc-sine law. But what happens when you have finite time? So something called, and these are challenges to measure, because these are not for long time scales. You cannot average so easily. These are transients. Reliable generic information is not easy. So basically, you define something called skewness, which is just, this is a classic definition of skewness, where you have these currents and their cumulants. This is well known. But you can also see that for overdamped non-equilibrium processes, these scale as t. This is shown in these papers, and this scale is t square. So this tends to t to the power half for small t, which means this is 0 for, so delta S is like Gaussian level here. And for large t, this goes as this, minus half. And both at large t and small t, you see that skewness should go to 0. What happens, however, in the middle? So there is some possibility that you would actually get a finite skewness, because you have 0 and 0 at both ends. And that is exactly what we saw. We essentially build up this current using some basis functions. We made some arbitrary currents with different choices of the C1, C2, C3, C4, and we saw that indeed there is finite skewness. And there is also a measurement time interval where actually that skewness maximizes. And we check that at lower T, upper T and lower T and all, they actually are proper. Okay, these are the results. So now what we actually use the entropy current. For particular values of C1, C2, C3, C4, we can actually get the entropy current. And that when we do, we actually see that, look at T plus, this is maximum time, T plus is, you would expect at long T and short T that on the long run, these would be equal, 0.5 plus T plus, you should have equal times over the average and below the average. However, we see that as you increase the degree of non-equilibriumness by changing the amplitude of the noise, you actually see that you get more and more times that the particle spends below the average. And there is also a measurement time interval where that skewness maximizes. That actually maximizes. This is the highest skewness that you get, and that sort of is dependent on what is the sort of time interval that you're measuring. And this is the T max, that is the maximum, what time you get the maximum entropy. That is also measured. That also changes. These are all verified by experiments, and we actually see very good match, pretty good sort of decent match. You can see that as you change the amplitude of the noise, you actually get these optimum times where the current fluctuations will be below average. Most of the time it will be below average. So the takeaways are very interesting. Most interesting, I feel, is of course, so the farther the particle is away from equilibrium, the more probability that you would find the fluctuations of the current to lie below average, below 0.5. And we also did it so this was a linear case, right? But then you can have situations where you have nonlinear cases. You can have bistable, you can have quartic. So if you go outside, Vishwajit has a poster explaining all this. So we actually saw that even in those cases, you do have this skewness finite. Discrete space systems, where like quantum jumps, where you do not have continuous currents. In discrete cases, what we saw, that it diverges at T tends to 0. That is not the same as just Gaussian current. So then again, if you do shorter scale measurements, they still tend to lie below average. But this is what is really fascinating, that the nature of the fluctuations actually depend on the time that I'm measuring them, which is so much like what you have in quantum mechanics. But what is even more fascinating is that do our molecular motors actually optimize their time scales? Do they know? That is why we have so efficient machines inside us. Right, so then this was the paper, and just a continuation of that, I said that for long times we get arc-sine laws, and arc-sine laws are all over the place, like fluctuation of stock prices and dynamics and all kinds of things like that. They're very, very prevalent. Anything where you have stochasticity, you have arc-sine laws. Here what we have, the arc-sine law comes in the cumulative probability distribution. Again, for T max, for T plus, this is the last time the time series change, and the maxima. These all obey arc-sine. So these are just a continuation of that. In fact, the previous work was born out of this. An MS student proposed this, and he looked at this, and then we suddenly, looked at the data carefully, and then we saw some very interesting stuff. What we saw is that the more farther you move from equilibrium, converging to the arc-sine law takes longer time. So this is basically a deviation from the arc-sine law. And you see that as you go farther and farther from equilibrium, it takes more time for this to reduce. And this was again done for the stochastic, this is for the first law, this was the overall, this is theory, this is experiment. This was done for the bubble again, so this was the probability distribution I was talking about. So you see this is with the bubble, it becomes constrained, and you also get a skewness directly. So here as well, you see that the deviation is, so for the bubble, remember, reduces entropy. So actually the convergence is faster. So that also you check here. So that is basically, the end of the story. So this was the paper. And again, last year, so returning the roots again. So what am I talking about? I'm coming back to where I started from, this. But the difference is I drive one of them with OU noise. So it becomes non-equilibrium. The question is what happens to the other? Can I induce non-equilibrium by hydrodynamic interactions or whatever? Is that possible? Endless possibilities, because you can actually look at molecular motors, machines, engines which work like this, not been done before. Viscoelastic medium, and so even you can make this problem in many ways. You can put this in viscoelastic medium, in non-equilibrium. You can drive and see what happens. Yeah, that's it. Thank you.
Thanks, Arun. So we can take one or two questions. Yeah. Go ahead.
So to quantify the non-equilibrium, can you define some kind of effective temperature?
That A times 0 is what we define actually.
Okay.
That A is the thing that we are saying. That is what we do.
Yeah.
So in terms of the measurement with respect to the bubble problem, very fascinating. You actually have the other trapped particle which is kind of displaced as a function of this particular bubble.
It is basically moving towards the bubble. You see the probability, there's a skewness, right?
Yes.
So it tells you that the trap center has moved somewhat.
So in this particular case, you can pick up the fluctuations
of the particle.
Of the particle with what specific method? You
same thing. No, I mean so that is like again a 2-laser problem, because you grow the bubble using 1 laser, and the particle is trapped using a 2nd laser, and the detection thing is with that. So there it's a issue, because if you come really close, then the drag force is so strong. I mean it will just suck in. Then that's an issue. So.
Because the optothermal aspect would overtake the optical.
Absolutely, there are much stronger things. So those are very strong. But here also you crank up the laser power for your trapping laser and ensure that it is. So initially it was interesting. So that's very details. But so if you are assuming they're in the same Z, if they are slightly up and down, so what Shubhra was saying, the student who did this, was that initially he was getting no sign of the bubble, which actually means he was sitting on some kind of a no-flow zone. And then, because that was not, so you leave the particle and nothing happens, and then there's no flow. So you optimize that. So you lose a lot of particles in the process, right? You trap, you lose, you see how quickly it goes inside. When you know that it's happening well, then you do the measurement. The thing is 100-second data, Pavan, for that long. So that is interesting.
Is that the trap still obeys the...
Yeah. That, there is now the potential is effect. No, there is that is the whole issue, right? Because we do not have the analytical solution, but we do check the stiffness. It comes to be okay, but whether we can use that, because now it's an effective stiffness, so it's no longer optical gradient force. So there is an effective thing, of course.
Okay, so maybe we can continue later.
Yeah, I'm there in the whole day. So, so Vishwaji's poster, I didn't talk about that bistable and quartic and things at all. So all details are there. So please go, and I think people have looked at it. Flash talk as well he gave. So thank you, Dan. It was a pleasure.
Okay, so the next talk is by Shamriddhi from ICTS, and he'll talk about scalings in active turbulence and Eulerian and Lagrangian perspective.
Battery is there. It is side change. That's okay, I can use my LG. Okay, so Thank you very much to the organizers, Pinaki and Arnab, for inviting me. So I'm going to talk about, active turbulence. So as you will see in a minute, I'm going to talk about bacterial suspensions, but from the perspective of someone who works in high Reynolds number turbulence. So I think sort of the biology and the biophysics aspects of this might be washed out very quickly. So just as a preamble, what do we, so at least in the context of this talk, what do we mean by active matter? So we are talking about systems which have agents, which consume energy, and they're sort of and they're out of equilibrium. So in a short summary, these are things which kind of move, and there are a whole bunch of very nice papers, reviews, etc. Some of which not certainly an exhaustive list, but a biased list, which I highlight here. So it turns out that this sort of phenomena goes across several length scales. So you have things at the meter scale, all the way at the level of a few microns, and that's where I will be focused on. So for this talk, and I don't really know, no, I'm pretty sure that most of what I say will not apply to things which are further up that scale. So in this talk, we will essentially look at dense bacterial suspensions, and just for clarity, and this is what I am familiar with. So these are suspensions which could be either of Bacillus subtilis, and that's because the early sort of experiments and or the results, as we will see, on which the work is based, were done with these suspensions, and more recently, and I'll sort of use this as a crutch. We have been working with Shashi Thuthupalli at NCBS on the system of E. coli bacterium, and I'll show you a little bit about what we see there. So this, as I mentioned, so it wasn't really the first paper to talk about such suspensions, but it talked about these dense suspensions in a language which is kind of familiar to us. And they talked about these low Reynolds number flows of these really dense suspensions, and you will see in a minute, that these kind of remind us of an analogous problem coming from a very different world, from a very different sort of scale separation. So, so the question that one sort of begins with at the 0th level is, how do I start to think about modeling such suspensions? So there are essentially two approaches, and Madan sitting right there as an architect of the approach that I'm not going to take. So one particular approach would be, to use agent-based models, and then, so the VICSEC model for students could be one of the starting points to think about how you construct such agent-based models, and then, you add in more complexity, you add in more physics to what these sort of individual agents should do or look like, and then you then sort of start to be more sophisticated and think in terms, within that microscopic approach, think in terms of particles which have certain properties, rods which could be polar, which could be apolar, etc. And then you get several, so this is from a recent sort of review by Barr et al. And then you see that this sort of approach, taking care of individual agents and then coarse graining at that scale, sort of gives you results which, or leads you to a theory which is reasonably robust for a wide variety of problems. So that's not the approach that that will be in this talk, no surprises. And what I will be looking at is a more macroscopic approach. So here's, for example, a movie from the experiments that is going on in Shashi's lab with one of his students and my postdoc, who you'll see in a minute. And the approach is, if I zoom out a little and then I start observing these flows, they seem to be nicely swirling, chaotic, and in particular, they look kind of turbulent to sort of give the game away, right? But this, again, remember, is really low Reynolds number, not the sort of Reynolds number, for example, yesterday that Jeremy was talking about. So the macroscopic approach sort of lends itself to a continuum coarse-grained hydrodynamic description and a coarse-grained velocity field just technically, but we don't need to worry about it too much right now. I'm sort of in the framework of what would be called dry active systems. So it sort of lends itself to a coarse-grained velocity field of the bacteria, which has a Navier-Stokes-like description. And since there won't be time for detailed derivations, but just sort of proof of the pudding. For example, I'll show you what the model is. I won't cheat that badly. But if you look at that coarse-grained model and you start sort of solving it, simulate it, you get a flow field which sort of looks very much like what we are seeing in the lab. So in this talk, the bacterial suspension will be treated really as a continuum two-dimensional fluid, and we will see at those scales with that description how far do we get. So this was sort of course, this sort of analogy was not noted by us, but especially again, this is not an exhaustive list, but the paper that was the starting point for me was from Julia's group and Ray Goldstein, and what they noticed was this formal similarity A from their experiments with B. subtilis and the continuum model, which I will show you in a minute, the fact that they sort of capture things well at the length scales beyond the bacterial length scales, and the formal similarity, for example, if you look at a really high Reynolds number two-dimensional flow. All right, so this is from the review paper by Guida and Beck. So this sort of gave rise to this jargon. So this sort of familiar, the fact that the two look similar gave rise to this term active turbulence, and I can't be sure whether it was introduced in this paper or before in the earlier PRL by but this sort of gave rise to this field, and just very recently, last year or so, there's a very nice review paper which focuses just on these aspects of these systems. So this sort of leads us to a couple of reasonably naive questions. So the first question that we wanted to tackle or ask in a very sort of simple-minded fashion is, in what sense are these low Reynolds number flows turbulent? I mean, active turbulence is a nice word, but what do we mean by turbulence here? And second, and this is of course clear, is that there is an emergent complex flow from the collective behavior of these dense suspensions. How is it beneficial to the poor bacterium? Why does it have to sort of organize itself in the way it does? So these questions sort of were grappled with with Chidatta, who's a postdoc at ICTS, Rahul, my former grad student, he's now a postdoc at OIST, Martin, also a former student, he is now a postdoc in Genoa, and I'll be sort of covering some of the results that these guys sort of had. So okay, let's go back. So the hydrodynamic approach, and I'm not going to justify it, but especially the students, we can discuss it over the tea break, essentially gives rise to this with various levels of simplification to this sort of equation. So firstly, it's an incompressible field approximation there, of course, in the dense limit. And then we write down this sort of non-momentum conserving equation for U, which is the sort of the effective velocity field of the bacteria itself. And just to set things clear, this is the only term which I'll worry about, which is the energy injection or the drive or the level of activity or how well fed the bacteria is. And for a theorist or for us doing simulations, this alpha is a number which varies in a certain range. And the reason this range is taken is that one is able to, I won't show you, but we can discuss this, one is able to map these numbers to actual velocities, which, what we saw from various, reports, experimental papers, was that these bacteria, in the two bacteria that I'm talking about, have velocities which are typically of this order. So our alpha will be constrained to be close to what you actually see in these systems. So let's begin with the first question, which is, in what sense are these low Reynolds number flows turbulent? So what do we know? So when I talk about turbulence, I will just talk about two aspects of turbulence. There are a few other aspects that we've looked at, but I won't be talking about them here. The first is scale invariance and their universality. So these will be defined in a bit, but what I mean is, so for example, in high Reynolds turbulence, independent of what sort of fluid you use, what sort of experimental apparatus you have, one does see a certain universality in how the kinetic energy is distributed across Fourier modes. All right, so this is all that the energy spectrum implies, and there is this sort of famous Kolmogorov prediction. This is for 3D. I mean, in 2D you have an analogous result, which sort of says that you always have a k minus 5/3 spectrum. So there was this very nice paper by Bratinov, Jenke and Frey in 7 years ago, where they talked about, where they showed, and these results were already there in earlier experimental studies, but they sort of put it all together very nicely, where they showed that as you change activity, so it's the same measurement of the distribution of kinetic energy across Fourier modes, what they show is that it has a power law, but that power law is non-universal, and the exponent or the power law keeps changing as you tune the activity of the bacterial. The other thing, that I'll sort of look at very briefly, for example, another telltale signature of a real high Reynolds number turbulent flow is the fact that there are large tails in, velocity increments or gradients, and this is sort of, brushed under one big carpet called intermittency in the field, right? So again, this is experimental measurements and continuum theory from Wensing's paper, and they clearly show, and in the supplementary material, they clearly talk about the fact that they detect no intermittency in the bacterial flow, either in experiments or in continuum modeling. So such studies really suggest that bacterial suspensions are not truly turbulent, but what we will now show that this is perhaps partially correct, and that there are truly inertial turbulence features which arise in a certain asymptotic, and you can sort of talk about a critical activity. So sorry for the best here, but I'll go through this slowly, but it's fine if we just stick to the essential results. So what's the calculation? I mean, this is sort of a very familiar calculation for all of us who do turbulence. So essentially, what we do, what Siddhartha, Rahul, and Martin did was you begin with the equation, and all we are after is what is this exponent delta? Is it universal or not, right? I mean, this was what we had, what I'd shown in the previous slide. So with these definitions, and again, there's a matter of detail because these equations don't close at the second order. So I'm after a second order correlator. This is a nonlinear system with u dot u. So there is a closure problem if I'm going to look at the second order moment because the third order appears. So what we do is use what's known as a quasi-normal approximation, which is close the system at the fourth order and then go back. It's a sort of technical detail which I'm happy to discuss. And then, lo and behold, so what one can sort of define is a relation between this object, which is the energy flux, so it's the integral of how much energy you're advecting across modes, and then you can sort of close this equation. So I'll come to the results without doing too much about this. And then what you do is you take the alpha, which is small limit, and then you can argue, because of the way the spectrum is, that the large scales are not energetically favorable, which, for people who are interested in the calculation, this sort of says that there is no effective time scale in the problem, or that it's a constant time scale, unlike real turbulence. And then when the dust settles, you can actually do a rigorous calculation and show that the energy spectrum has this form, where, as you see, delta, the exponent, is activity dependent. So there is nothing universal at at sluggish bacteria or bacteria which are lazy like me. So let's see what happens when the bacteria are less lazy and they're more energetic. So that's in a different asymptotics, and what one does is, and again I realize that it would be hard to go through the calculation, so I'll probably focus just on the result. So what we assume, and this is real in ansatz, is that now as delta, which was the exponent, starts becoming positive, the larger scales are feeding in energy as your activity increases, and this is clearly seen in experiments. And so you have an effective time scale which we measure. So this is at low activity, there is the effective scale dependent time scale, but as alpha as the system becomes more active, you end up generating a time scale in the problem which is both dependent on the fact that you have an alpha induced noise in the problem, so it's an ansatz, so we just take it to be a 1/k noise, and a local flow induced time scale, which is something that we are very familiar with when doing turbulence. And for no good reason, except that's the sort of trick which seemed to work, we sort of conjectured that the effective time scale is really the geometric mean of this. So the interesting thing is one can also take a golden ratio of this and come up with a very similar result. And what we then see is that at large alpha, at high activity, the energy spectrum has a constant scaling function. So we move from a spectrum which has a scaling which is a function of the activity, to a regime at large alpha, and I'll talk about when this crossover happens in a minute. But the important thing to note is now we have a unique scaling exponent as opposed to at low alpha, where the scaling exponent is a function of what sort of bacteria you have in your system. So of course, there are numerical checks to all these assumptions, and they kind of bear out the scaling relations that one has. And essentially, when we calculate the energy spectrum, we see that as we increase, so this is for low activity, which has this, as you increase activity, suddenly you get a clear universal signature in the power law that we have. So of course, what I presented is much more of a soft sort of phenomenological argument, but you can, or rather, Siddhartha, Rahul, and Martin did do a very rigorous derivation of this, and one can actually derive it, including the exponential tail of these two-point correlators using closure arguments to actually come up with the same -3/2 result. So in essence, just to sort of summarize this part, we do see that there is a critical activity, and now I'll come to what that critical activity is. So there is a critical activity which the theory suggests is a number which is order -10. And it's a sort of semi-complicated way, so we can discuss this later in front of the blackboard, how this -10 number is achieved, where we predict that the scaling exponent for activity, which is so all of these have negative signs, so that's why it's greater than. So you have an alpha dependent exponent delta, again just to remind you, delta being the scaling of the energy spectrum, and beyond that critical activity you have something which is stuck at -3/2. All right, so this is from our measurements, from the simulations, this is the transition that we observe. You will notice that the simulation suggests the transition at around -5 and not -10, as the theory suggests. We looked for a factor of 2 everywhere, both in our simulations and in the theory. We haven't yet seen, and so we are being faithful to what we hope are right calculations. So now you see, I mean, if you just compare to the high Reynolds number picture that I showed you, and this is, by the way, this is a whole bunch of experimental data from various sets of people, what you see is that bacterial flows beyond this critical activity are much closer to the way we think about inertial turbulence. And as I said, I'll just sort of look at 2 features of this, and the second feature is the issue of intermittency, which was earlier measured not to be there. So now that we had this alpha C sort of prediction, we went ahead and tried to look at intermittency. So what I'm doing here, for example, so these are sort of color plots of the vorticity field. And as you go and start to detect extreme events, the top panel is for very mildly active things. Unfortunately, it doesn't really show up very well. The lower panel is for much stronger active turbulent flows. What you see visually is that that there are extreme events which show up only when you have an activity beyond this critical value. And then you can actually sort of quantify this by looking at the distribution and the kurtosis, etc. And then you find, so for alpha less than, again, the same -5 from independent calculations of intermittency, you find that it's 3, so things are non-intermittent. But as soon as as soon as the bacteria becomes more energetic, you find a sharp rise in kurtosis. So, of course, in turbulence, we have some idea of, the scaling of this. We haven't looked at that yet. And then you can also sort of condition it on scale separation, but that's a matter of detail. The big picture is that, again, when you have things which are really active, the suspensions become much closer to the world that I come from, which is sort of high Reynolds number flows. And just one more sort of minor point on this is, and this sort of is slowly getting into the question of mixing and what's the deal for the poor bacteria, having done all the hard work. So this makes a nice transition. So what we also sort of looked at is essentially setting up twin simulations. So you have system A and system B, and they differ by a very small perturbation. Eta is a white, uniformly distributed white noise applied to every point. And what one calculates essentially is the difference of these two fields, which are minimally different at t equal to 0, and then try to understand how the how these different spreads. So it was a trick that with Shubhro and two other students of ours, Sugan and Dheeraj, that we had used earlier for the Euler equations. So what one sees, and this is quite interesting, is that if one looks at the sort of decorrelator in our language. So, Jeremy touched upon something very similar yesterday in his talk when he was talking about spontaneous stochasticity. So we are still in the sort of chaotic regime where things are exponential. So when you measure this phi of t versus t, so it's a semi-log plot for different activity, you of course see this very nice exponential growth followed by saturation as A and B become uncorrelated at some point. But what was very surprising to us is if you actually measure the Lyapunov exponent, I mean, the two curves are basically the same, but non-dimensionalized in different ways for some reason. So let's look at the black curve, which is just lambda. What you see is that, again, at around 0.5, I mean, this actually looks closer to -3, but I'll still claim this is the same -5 that I've been pitching for. You see that the Lyapunov exponent saturates and things become maximally chaotic and stays that way beyond alpha C. Now here, I mean, the earlier two things I sort of pitched for turbulence-like approach to understand the suspension, but this is certainly very different, because if you play the same game with Navier-Stokes turbulence, you have, colloquially speaking, an unbounded growth in the chaos, because the Lyapunov really scales with Reynolds to the Blau, where Blau is very close to 0.5, depending on which sort of theory you want to use. So activity is not exactly mappable to the Reynolds number, is what one kind of takes away from this message. And then you can also look at the difference of the spectrum. This is in the Lorentz style, and try to see how similar the growth is. Very good. So beyond critical activity, so when I go beyond this critical activity, what does it mean for the suspension in terms of mixing? Because at the end of the day, my fluid is a living fluid. And so the self-organization or the emergent flow that happens in this fluid must have some implications for what constitutes this fluid. So So for this, we essentially take, what would be a Lagrangian approach, and Jeremy introduced this yesterday. What we do is, in these sorts of simulations, we now randomly sort of feed the flow with tracer particles. Again, I'll just be reporting the theoretical work, so this is something that we are also trying to mimic in Shashi's lab to try and see this. So what we find is the following, and this slide should be, this could be the kind of take-home message, even if you want to avoid the details later, which will come. So for example, let's look at this, if it's sort of kind of clear. So here is a sample set of trajectories which are all artificially sort of put in the center for easy visualization. So as you see, if you look at very small activity, so which is -1, so the bacteria is in the ballpark, let's say, of speeds of 20 micron per second, roughly. That's the suspension that we have. Then you see these sort of very meandering trajectories which sort of are reminiscent or pictorially, and I'll quantify this, are like random walks and normal diffusion. As you start sort of pushing the activity and you look at this blue thing, you start seeing that the paths are being straightened out. Right? So for a really active case, alpha -6, this is a good example where we sort of, separated the bunch of trajectories and found that there are trajectories, and a very finitely significant fraction of them, where they essentially move in straight lines, or largely move in straight lines, whereas there are a bunch of trajectories here which are essentially diffusive, and this sort of color map is a good way to sort of visualize what this is. And these, we realized, were related to another thing, and I'm not going to talk about this here because this is sort of takes me far away from bacteria a little. These, we found, were related to these emergent structures in the flow field. And these, have also been seen when we sort of checked with earlier experimenters like Rick Eller, etc., who sort of were kind enough to share their experimental data with us. That there are these sort of, very big, sizable patches which stay long, which are neither vortical nor straining, as people in 2D turbulence like to talk about, but which have these very streaky behaviors. So what these streaks do, so you can sort of separate the flow by going in and sort of reprocessing your data and try to find where the trajectories emerged. And what we see is that if they emerge in streaks, then they have this very coherent sort of bundle-like motion, which allows them to have the sort of trajectories that we just saw. So what does it mean in real terms? I mean, this is the sort of this is the kind of picture that emerged from the simulations. But in real time, what this means, what this implies is, for example, if we look at the mean squared displacement, which so it's a standard definition of the mean squared displacement. So we looked at the mean squared displacement from Siddhartha made these, so he insists that I have this. So they're quite beautiful to illustrate the point. So you look at mean squared displacement of these different trajectories for different levels of activity, and then you ask the question, what is delta x squared? So short time ballistic, that's that's a given. But at long times, is the exponent 1, less than 1, greater than 1? Okay, so that's the question that we are asking. So when you have low activity, and we were not the first people, so Ashwin Joy and his student Sanjay from about a couple of kilometers away from here at IIT Madras had this very nice paper where they actually measured it, and this was our measurement, and they showed that at small activity, you sort of have a linear scaling, so it just goes boringly from ballistic to diffusive behavior with a certain crossover, and this sort of crossover perplexed us because at that time we were sort of wondering about what alpha C does. So at low activity, this is all boring. That's a sample of the trajectory. And then we discovered these sort of experiments by Galerial and Bayes' group. And they sort of said that, look, in our experiments with the same system, we find evidence for Levy walks. And then there were a bunch of papers around the same time. Madan probably knows some of them. I've sort of given a short list of these papers where is it Levy walk, is there anomalous diffusion or not, and different sort of experiments. It wasn't completely settled. But the question was, why has it remained undetected in simulations where the data presumably could be cleaner? And the reason is that the simulations before were all performed with low activity. So this is an example from Ashwin's, where of course he sees the behavior which is just T. But then when we sort of started to look at the swimming speeds, etc., for the experiments that Gill and group were doing, we saw that their swimming speeds or the level of activity of their suspensions was in the ballpark of what we called alpha C, or the critical activity. So we pushed this idea and we started measuring the mean squared displacement as a function of activity. And lo and behold, the minute the sort of suspension turns really active, you go from the diffusive to the super diffusive behavior which some of these experiments suggested. And of course the trajectories, and this was very close to what the group in Israel reported, had all these sort of features of Levy walks. So just to summarize, so there's issue of anomalous diffusion in these suspensions, but it's anomalous diffusion which only shows up beyond the same critical activity -5. So and what we did was just to try and understand whether it's the same effect. So anomalous diffusion mediated via Levy walks. We sort of looked at the trajectories very closely, and so there is a mathematical bootstrapping that one can do, which is you forget about anomalous diffusion, but you look at the Levy walk statistics, which have certain power law tails. And then this sort of ought to satisfy certain relations with these exponents. So this was kind of slightly more comfortable, or made us slightly more believing in our data. So we sort of again looked at the Levy walk statistics of these bacterial trajectories just to close the argument and see that indeed the picture is self-consistent for anomalous diffusion at activities which are much larger. Of course, one can ask a more direct question to this, which is forget anomalous diffusion, but you cast it in the sense of a first passage problem. So you asked yourself, what's the statistics of things reaching an absorbing boundary condition at some radius r away. And so using the same idea, just to again, because the results were a bit surprising, we wanted to sort of test it out, different approaches, just to see it holds. And what we sort of, this is the standard sort of distribution that one gets from effective Fokker-Planck with absorbing boundary conditions. And what we saw again is this change in behavior from normal to super diffusion, also in the first passage statistics, as we go from, the threshold is somewhere at -5. So as we go from -4 to -6, there's a clear signature. So let me end with some conclusions. So things. So I have some time. I thought, yeah. So things that I did not discuss, but happy to discuss because there are people here who might be interested. So I talked about the emergent universality in scale invariance, and the onset of intermittency and maximally chaotic states beyond a critical activity. Again, this and the universality of scale invariance is very very inertial turbulence, whereas in my opinion, this is not. We also, I didn't discuss, but we talked about these sort of new features in the flow that we detect and that we see in experiments, which allows some of these phenomena to happen. I didn't explain the connection very clearly, and that there is, beyond the critical activity, there is anomalous diffusion. And quite interestingly, and I didn't discuss this because I thought I would not have time, is the fact that there is a certain, to use borrowed language from a different field, there is a certain dynamical heterogeneity, a phrase I first picked up from Pinaki many years ago. So to use borrowed language, what we noticed is that there is a dynamical heterogeneity in these trajectories, in the sense how you would do for a glassy system. You go to the ensemble and then you pick, also Shahid's, and there you pick, on a subset of trajectories, and you see that they are really different from the others. So right now, some of these things are being tested by Siddhartha, who you saw. Suresh is a grad student, and Shashi. And in the experiments, we are now looking at various problems related to what I discussed, but also, and by chance, we sort of stumbled upon what's the role of small little polymers as we kept feeding the bacteria sugar in this sort of anomalous state. So I sort of end with this question, which is where I began with in this business, is whether active turbulence is really light fluid turbulence. Not entirely sure. Okay, so thank you.
Thanks, Shamridhi.
Yeah, Rajesh.
Forgive my naivety about this, but when you showed this comparison between the inertial turbulence and the active turbulence, the distributions that you were comparing earlier, and you said you didn't see intermittency. The studies earlier didn't see intermittency. Yeah. The tails really kick in after about 3 orders of magnitude drop, and the numerical study or whatever it is.
The experiments didn't go that far.
Is it, they just miss it, or did you have to do something else to really capture the intermittent tail?
So with the same sort of, in a completely naive language, the same y-axis band, if you like, the tails did kick in only with alpha. Now again, for in high Reynolds number, so different world, inertial turbulence, you do see these tails spreading as a function of Reynolds number. But once it's sort of fully developed, you do have always fat tails. But here there is really, in the measurement of the kurtosis, which is a very sort of sharp measurement, so in high Reynolds, etc., you'll have a scaling with Reynolds. I mean, we actually don't know what the scaling with alpha is. We didn't get there. But here you do see a sharp transition from a kurtosis, which is 3, Gaussian and nice, and that at critical activity, it suddenly sort of shoots up and starts growing. So the question that you raise can always be there, but at what we have seen, we and other groups, I think it is an onset of intermittency and not something which was very mildly present and not picked up. This would be my answer. Yeah. Thanks.
Pawan and then Madan.
In the context of the experiments, what you're talking about, the anomalous diffusion thing, how sensitive are these experiments to the boundaries, what you actually confine the bacteria in? Because there are cases where, for example, if you have periodic posts or something like that, you do observe some kind of anomaly in diffusion. Would you observe such kind of effects if you take your boundaries to be specific?
Good. So what we've done is, the usual cheating. So in our case, it's periodic boundary conditions. It just helps with the numerics. But Gill, etc., of course, had boundaries. I mean, their measurements were quote unquote in the bulk. So bulk being a very tiny region anyway. So I actually don't know whether it was a boundary effect, but certainly in our case, there is a complete absence of boundaries. So this is really like an infinite bath of bacteria. So in the simulations, it's really not coming from there. So experiments, you might be right. Something maybe in the lab now that we have Shashi's set up, we could look at this. Thanks.
On a slightly broader context, if you see the per se the definition of active turbulence, can one look at this as a driven active matter? Or because in order to actually drive the system to turbulent regime, you need to actually force this to a certain out of equilibrium condition. Would that be a connection also possible?
Yes, it's driven, of course. I mean, I didn't sort of show you, but for example, you do see the kicking or the injection of energy, the drive, if you like, at scales which are comparable to the bacterial scale. So from there you can construct the flux argument, etc., how the energy is going. So sure, it's a driven active matter, and it's sort of completely out of equilibrium, but the drive is kind of very different from how you would drive, let's say, a soap film, for example, in the sense that the scale separation between the drive and the smaller scale you can resolve, which is still at the continuum approximation, there is a lack of scale separation there. So it's something that has been observed. I can show you a little bit the data on that, which is not in the slide. So it's the scale separation which is the problematic thing here. You're right.
Oh, yeah, thanks for the really great talk. I have a broad question about this field. So you focus here on dry active turbulence, but there is another body of literature which has the same name, but which is actually completely different set of equations. Is there any reason why you'd like to focus on dry rather than wet? That's my first question. And second question, when you try to really describe quantitatively the experiments, when you try to map your theory with experimental data, is there any decent way to choose whether you'll describe wet and dry, or is it something you can completely switch between?
Okay, so wet and dry, the first question, the answer is just because, a couple of years ago when we started looking at it, the equations for the dry system, although it's non-momentum conserving, as you know, so we sort of got rid of the solvent, let's say, with which it's exchanging momentum. But that was something much more familiar. So I come from a Navier-Stokes Reynolds on the turbulence. So formally, it sort of appeared a good starting point in this sort of for me to get into this business. And what we were able to sort of, what was appealing was the Dunkel, etc. results. And then there were further results by Christian, etc., on a similar model with rescale viscosities, where the mapping with the experiment suggested. I mean, even the incompressible thing is an assumption, which is a dramatic assumption, right? Which sort of said that this seems to do a good job. So now coming to the mapping of the parameters, because that's really where the problem lies, is that the early, so what we did was we looked at, so once we fix, there are parameters beta, etc., hanging around lambda, which has slightly more physical sense in terms of pusher-puller, so that was easy to fix. But then the important thing was alpha, the drive. So what we did was you can fish out, so from the equations with the sort of coefficients that you have, one is able to fish out typical sort of velocities and length scales in the problem, the polar velocities of the bacteria. And for every alpha that we do, we look at those velocity numbers, looked at the existing experimental stuff, about 2 or 3 groups, otherwise it was becoming very confusing. And then in a notebook, okay, this is this velocity, and once that assumption is made, so we began with the length scale, which you get from gamma 0, gamma 2, some combination, I forget some of those combinations, with the experimental sort of setup, and from there we get the alpha to map to the velocity range there. But of course it's not a very precise mapping.
But could you do a similar type of mapping for wet active turbulence?
This I'm not sure.
Okay.
I haven't really sort of looked at it yet, but we have to get there because of this polymer business to soon start thinking about the solvent.
Okay, thank you.
Thanks.
Yeah, so a similar question, but before that, lovely talk, and so Yeah, I guess the proper way of doing this is to have a two-component system where you have the density of the bacteria and the background fluid.
And the solvent,
right?
yes.
But as you say, there's some formal correspondence between this and the Navier-Stokes equation, so you decided to look at this. But also in sort of connecting with regular turbulence, I thought the sort of standard Yakot and Orsag way of forcing the thing was to generate sort of forcing in the larger scales, and then there's a well-defined separation of scales at which dissipation happens. Here you're driving it at the smaller scales. So that itself is a bit, the analogy is a bit, analogy between this and regular turbulence is a bit shaky right from the start, isn't it?
So yes and no. So for example, if you look at 2D soap films, so I understand the Yakot-Orzak argument you make, stochastic forcing, there's a scale invariance, so in Berger's, the one-loop calculations actually need that. But if you look at soap film experiments, so 2D turbulence, and this sort of gets into a minefield now, the analogy gets worse. So 2D turbulence, because of additional conserved quantities, has this inverse cascade. So in the last sort of 15 odd years, there have been various soap film experiments and simulations where you're forcing things at very small scales to kind of resolve the inverse cascade. Now, there is actually not really a strict inverse cascade happening in this problem because the flux has a very tiny but a distinct dependence on pi, on the flux has a distinct dependence on the wave number, which sort of comes out in the closure calculation, which you need as an integration constant to fix the spectrum. So the analogy is still, this was the last.
So the concern I had was about, there should be a lot of density inhomogeneities generated as a consequence of this flow. And so alpha would be dependent on the local density. And because you have taken it to be a constant.
We've taken it to be a constant, yes.
So isn't that another issue to sort of tackle?
It's another issue. So what, so the thing that we are sort of looking at now is first on the wet part to actually make the system coupled and momentum conserving, because that's something which doesn't sit very comfortably for a system which doesn't conserve momentum. The inhomogeneity in alpha is something which I understand sort of at a qualitative level, but it's something that Shiddat is measuring in the lab to look, so PIV measurements actually is what we are doing, to look at different distinct patches and then to see if that inhomogeneity, how strong is that inhomogeneity. It's certainly there because already we've sort of kind of washed away the density fluctuations in the divergence U0 case, which is why I pointed out, right? So there's been two levels of cheating, which is the incompressible case and the disregard for the what happens to the momentum. So what we sort of done is in a way think about it like how you sort of put in the dissipative term and essentially integrate out the degrees of freedom which would have conserved it. Yes. So there is a strong element of cheating there.
Maybe last question. There's one more.
I have a technical question regarding the Lyapunov exponent and how you compute it actually, because I understand that you need to have two different time evolutions, one unperturbed and one perturbed, and then you need to know that which one is perturbed and by how much, and then take the ratios of the two different trajectories altogether. And then you have a multi-particle system, of course. So how do you keep track of all that while the computation is done, or the measurement is done actually?
So, right. So this is actually doing it in a slightly different way. What you said is, of course, So what we do is no particles, so this is a continuum fluid. So we have system A, which is in some sort of non-equilibrium stationarity. Then we create a copy of this, and we introduce noise everywhere. From a uniform, it really doesn't matter. So you can introduce locally a bit of noise, or you can spread it everywhere in Fourier space, in real space, it really doesn't matter. So these are identical up to that noise amplitude. So then what we do is essentially, Again, you can take any of the fields and see the evolution in time of this. So at large times, the two were, and these are independently evolved, satisfying the same equation.
Right.
Right. So, and the noise of Bayes and compressor, all those technical things.
And then this B, where you introduce the noise, is that just one kind of noise that you introduce, or do you have
at
to?
t equal to 0, let's say.
Okay.
At t equal to 0, these two configurations differ by delta. So as time evolves, we want to see how they separate. So at large times, I mean, if you expand this quadratic, at large times it's saturation because the two fields are uncorrelated. They've forgotten their memory. So that's why there was this normalization with the time scale, which I didn't explain. And so then there is this exponential growth.
Will this strength of perturbation affect the Lyapunov exponent?
So for the Lyapunov,
actually, I have seen a very strong dependence on this, and I'm stuck there. Actually, that's okay.
The best person for this part is, I think, Jeremy, and you should talk over the coffee break. But in this regime where we are sort of really looking at the chaotic growth, so once we've sort of divided out with the perturbation, the delta omega squared, etc. Again, it's something that Abhishek and others and some of us had seen for the spin system, then Shubhra and I for the Euler, etc. So in this way of calculating, we are able to scale it out, the initial perturbation.
I see. Okay.
I think we really need to stop now, so Shaurajit, you can ask your question in the coffee break. So let's thank Shamriddhi for a really nice talk. Okay, so we meet at 11:30.